So what's the launch? It's like 93. So why did she say
Hello, everyone. Let me first just remind you to take that fall exam survey. I sent it in a remind day before yesterday. It's just a quick question whether you intend to take the final exam or not. But if you change your mind, just go ahead and fill that out, because if you change your mind, you can always let me know by Monday whether through remind or through email that you decide to change your mind. But if you don't fill out the survey, I'm just going to assume that you're not going to take the exam. So I just want to begin to start planning the exam process of assigning exams to students who are going to take it. If you're face-to-face, then you're going to be taking it here in class. If you're virtual, then you'll take it through Teams. Okay. But yeah, most of you guys have filled out the survey, so thanks. Do you guys have any questions that you have? Okay. So today, I want us to do a little bit with continuity, finish up chapter 1. So we'll talk about continuity conditions, make sure you understand that process. We'll do a problem related to that. And then I want to focus our attention on related rates. I know we just got through with related rates with trig, but I want to talk about related rates from chapter 2 that involves more geometric shapes like spheres and cones. So we'll do, and cones are a little more involved because they're similar triangles. That's required for us to work through that. And then we'll also talk about, let's talk about derivative graphs as well. If I give you an F prime graph, can you gather information about relative max, relative min, POI, increase, decrease, and also can you match what the original graph could look like based off the F prime graph? So we'll spend our time today on those two topics. Okay, so I'm going to be working off of packet number 1. I think today I had the link for packet number 2, but I'm just going to kind of push everything back a day. So tomorrow I'll pick off problems from packet number 2, but today I'll do packet number 1. And then we still have tomorrow and Monday to review through material. So Tuesday will be a shortened class period, and the periods are kind of the order is kind of changed up. So this is what our Tuesday schedule will look like because of the 7th period exam at the beginning of the day. Okay. So let's look at we're going to look at number 15. This is off the packet here. About limits, about continuity. But before we do that, let me start off by just doing an overview of continuity. Okay, so. All right, so continuity. Let's say we had a graph. And the first thing we do with the graph is, if we want to determine continuity, we have to first determine, does the point exist? So that's the first condition of continuity, is looking for that, where that point exists. And the second condition is, does the limit exist? So we talked about yesterday how points and limits are kind of related, but they're also very distinctly different. They both involve a target point, but the point is more concerned about what's happening just at that physical location. Limit is more about, is the approach consistent towards a certain value? So let's say the graph looks something like this. So that's the second condition. Does the limit exist? All right, so if a limit exists, that means the graph is approaching the same y value from either side. Whether the graph exists at that point is not as important, or it's not important at all for limits. So what we do with limits is we pick points on either side and see if the arrows are headed towards the same y value. And if they are, then the limit exists. In this case, it does, right? Sometimes we have to dig a little deeper and use notations and having to look at the limit separately. And if we do that for one side, we have to use one-side limits. So that is where we look at the limit from just the left side, gather that information, and then we look at the limit as from the other side, gather that information, and see if they are in agreement. If they are in agreement, then we can conclude that therefore the limit must exist. Basically, this is a notation version of what we do with these arrows, right? So this diagram is showing that the point exists and the limit exists. But then in order to achieve continuity, a third condition needs to be fulfilled. And that is where we ask ourselves, does the point live where the limit lives? So the first condition and second condition's results have to be in agreement with each other. And we see that in this case, the order pair is at 2, the limit is at 1. So for this particular instance, the third condition would fail. So we would say for this graph, our function is not continuous. And we call this a removable discontinuity. Okay, because the third condition fails here. So that's how we determine continuity using this specific language. Okay, and that's what we're going to do when I have this problem for us, that we can just step through the continuity conditions. It kind of gives us a structure for us to kind of go through. And at the end, we can kind of just look at the results that we gathered and see which parts we fulfilled and which parts we didn't. So here's number 15, and we're going to work off of these conditions here. So here's 15. I'm going to just write the problem below here. We have a piecewise function, f of x equals now this piecewise function is we have to kind of understand what information is given to us. There's two graphs here, right? Y equals 4 and y equals x squared minus 1. But this y equals 4 is not going to display a full graph. It's just going to display a point. So that's important to understand, that this second piecewise is not going to give us anything more than the point. But the first piecewise is going to give us everything on both sides of 1. So to the left of 1, x squared minus 1 is defining that graph. To the right of 1, it's also defined by x squared minus 1. So on both sides, most of the graph is going to be contained within this function, this x squared minus 1. So let's go through our conditions and see whether it's going to pass all 3 conditions. So the first condition is that the point exists, and if you're trying to determine what the C value is, it's always going to be given to you within the restriction. So the restriction is always going to tell you where the focus of our center of our problem is. So in this case, it's 1. So we find f of 1. F of 1 is defined at 4, so we say f of 1 equals 4. So we have our order pair, that's squared away. Second condition, does the limit exist? Right. We don't do one-sided limits because it's the same function on either side of 1. It's x squared minus 1 as we approach from the left, is x squared minus 1 as we approach from the right. This is just a point, so this is done. We're just looking at that x squared minus 1. And because we're dealing with the same function on either side, we only need to write our limit statement once. Right? Now, if we had 2 different functions on either side of 1, then we will have to find the limit separately because we have 2 functions to work with. But here, there's really only 1 function. This is not really considered a function. The second one is just a point. So we're going to find a limit as x approaches 1 of the x squared minus 1. Okay, so how do we evaluate this? Yeah, just plug in 1, right? So if I plug in 1, I get 1 squared minus 1, which is 0. So that's a real number. So the point exists, the limit exists, but is the third condition going to pass? It's going to fail, right? The order pair is not where the graph is headed towards. So the third condition fails, and we say f of 1 does not equal to the limit as x approaches 1 of f of x. Okay, maybe this is what the graph could look like here. F of 1 is 4. The limit as x approaches 1 is 0. And we see that there is an obvious discrepancy here at this point. So we say that not continuous, right? Because we have removable discontinuity, that third condition is failing. That's why we have removable discontinuity. So now, based off of that, we should be able to make our conclusion as to our answer for number 15. So 15 says, which of the following are true? The limit exists. Yes, that's the second condition. We made that. That's definitely true. The point exists. That's also true. But the function is continuous at x equals 1. That's going to be false, right? Because all 3 conditions have to pass. And in this case, the first 2 conditions passing is not good enough. We need that third condition to pass. And so not continuous. So really the only thing that we can say are true is the first two statements here. F of 1 exists and limit exists. So anytime you see a problem involving continuity, I like to just go ahead and step through continuity conditions, and that way it kind of gives me a structure for me to gather all my information, and then I can read the problem and decide what pieces fit or what the problem is asking for me to find. Okay, any questions with continuity conditions? Okay, maybe after we hit all the topics, hopefully by Friday, we can circle back and just pick out problems from from the other packets that are referencing these types of concepts. Okay, so let's turn our attention to related rates. We'll do some problems with related rates here. Now, the unique feature of related rates is the fact that we have time kind of flowing through the entire problem. And because of that, we always have this d over dt that shows up whenever we're dealing with related rates problems. So it could be d theta dt, it could be dx dt, dy dt. Right? And today we're going to be talking about volume and surface area, so we're going to be expecting dv dt, ds dt. Okay, so here's the problem that I want us to do. Let's see, where's the handout? The half sheet here. All right, so we're going to do this problem here. This is number 42 off of the first packet. Okay, let's read the problem and then let's see how much we can. I'll go through the whole problem step by step. Okay, a balloon is being filled with helium at a rate of 4 cubic feet per minute. Find the rate in square feet per minute at which the surface area is increasing when the volume is 32 pi over 3 cubic feet. Note the volume of the sphere is 4/3 pi r cubed, and surface area is 4 pi r squared. So I like to begin with the equations and just get the calculus portion out of the way. I know that my derivatives are going to be used, so I'm just going to go ahead and find each of these derivatives. Okay. So we're expecting a dv dt, a dr dt, ds dt. And remember, pi is just a coefficient, so there's no product rule involved, right? All we need is power rule on the right side. Okay, so let's go ahead and find each of these derivatives here. So v becomes dv dt, or 1 dv dt. 4/3 pi, coefficients. It's going to hang out in front. And then r cubed becomes what? Yeah, 3r squared, but we also need dr dt. Yeah, every variable has a time impact. Okay. Do a little bit of cleanup. 3's cancel out. Okay, let's go ahead and find the derivative for s. S becomes ds dt. Four pi stays. R squared becomes 2r dr dt. Clean this up. Okay, so we got all the calculus out of the way. Now we're just trying to gather information, plug in, and find the missing variable. Okay, so let's go back and read the problem and see what information we can gather. Okay, so a balloon is being filled with helium at a rate of 4 cubic feet per minute. So what's going to hold that information? Okay, so cubic feet, we know that's volume related, but then there's minutes, so dV/dt, yeah, dV/dt. Now, is this positive or negative rate? Positive, right. We see some context clues here. It says being filled. We know this volume of the balloon is growing. So positive 4. Find the rate in square feet per minute at which the surface area is increasing. So what are we looking for? Are we looking for S? It says find the rate in square feet per minute. So which variable is going to be in terms of square feet per minute? ds dt. Yeah. Right? When the volume is 32 pi over 3 cubic feet. So that's just V. Okay. So let's see, we gathered all that information. We're looking for ds dt, so let's see how we can work our way to the answer. Okay, we're looking for ds dt. Let me highlight that variable. That's our goal. And we have that here, right? We have ds dt. So to find ds dt, I need radius and I need dr dt. It would be nice if we just had r and dr dt for us to plug in, but we don't. But do you see a path that we can maybe eventually work our way to our radius and our dr dt?
If you plug in volume, you could get from.
Good. So let's start here, right? Volume can help us get one of the variables that we need. So let's do that. So I'll replace V with 32 pi over 3, and we'll work our way to one of the variables that we need. Okay, if I want to solve for R, I'm going to divide both sides by 4/3 pi. Dividing by a fraction is the same thing as multiplying by the reciprocal. So if I multiply both sides by 3 over 4 pi, I can get this to go away. And really, I'm just multiplying this, right? So I get the pi's to cancel out. I get the 3's to cancel out. I get 32 over 4, which is just 8. Take the cube root of both sides. That will lead me to R. So that's one piece that we need.
And then if you plug it into the dv over dt equation,
That'll lead us to the what?
dr
dr/dt, yeah, good. So we have radius being 2, we have dv/dt, and so we're looking and seeking out another equation that can help us find another missing variable that we need. Okay, so we'll work with this equation. Okay, so dv/dt gets replaced with 4. Radius is 2. And dr/dt. Okay, clean this up. I get 4 times 4 pi, 16 pi. If I want to solve for drdt, I'll divide both sides by 16 pi. drdt stays, 16 pi cancels out. Now 4 over 16 reduces, but we got to be careful that pi stays in the denominator, right? It doesn't suddenly move up. It's going to stay in the denominator. So 1 over 4 pi. All right, I think we have everything we need, right? We have the drdt, we have r, and now we can just substitute those into our equation to help us solve for ds dt. So 8 pi r dr dt. Multiply, clean this up, pi's cancel out. 16 over 4 is just 4. And what's our unit of measure? Yeah, square feet per minute, yeah. Surface area is two-dimensional units, so square feet. Time is minutes, there we go. Any questions? Okay. All right, let's do another related rates problem, but now let's talk about cones. So this is number 47 off of packet number 1. Hold on. Okay, so we have a circular cone, vertex down. So let's go ahead and draw that diagram. "20 feet is the dimensions, radius 10 feet. Water is leaking out so that the surface is falling at a rate of 1/2 feet per hour. The rate in cubic feet per hour at which the water is leaving the reservoir when the water is 8 feet deep is." So here's a portion of the diagram that we're interested in. Just that little portion there. So here's the issue with cones. Here's the volume formula. The issue with cones is that we have too many variables in the problem. And the radius and the height are referring to the radius and height of the water level, which are both continually changing. Which means that if we find the derivative using product rule, we'll have all these variables with not enough information to replace them with. So the idea is that we want to create a relationship between radius and height so I can replace one variable with the other. And the way we do that is we use similar triangles to help gather that relationship between the two variables. So here's the radius of the water level. Here's the height of the water level. Those are both changing. What is unchanging, though, are the dimensions, which is 20 for the height and then 10 for the radius. So we're going to build a relationship here that's going to connect radius and height together. So we can say this. We can say radius of the water level is to the radius of the container as the height of the water level is to the height of the container. Cross multiply. Okay. We're going to pause a moment because right now we don't know which variable to replace with yet. We're going to gather some more information, and then from that information we can decide which is going to be the most efficient way of getting to our answer. So we'll pause for a moment here, and we'll go back to the problem and see what other information is given to us. Okay, let's see. First sentence, we have everything down here. Water is leaking out so that the surface is falling at a rate of 1/2 feet per hour. So what do you think that 1/2 feet per hour is referring to? Good, change in height. Also, we can tell that this is not going to be volume, right? Because you see just feet per hour. It's a one-dimensional unit. So it's either radius or height, but you see the word falling, so you know it's a vertical movement. That must be height, so dH dt. Positive or negative? Negative, right? Leaking out so that we know that height is changing by decreasing. The rate in cubic feet per minute at which the water is leaving, so we're looking for something in terms of cubic feet per hour. We know that must be dV dt, right? That's our goal here. When the water is 8 feet deep. That's just what? Height. All right, careful with this 8 feet. I know some students want to look at that 8 and start putting that into wherever they see h, but we have to hold on to, this is talking about the water level, right? The water level is still changing. So we're going to save this until the end, until we have a specific moment in time to deal with. But until then, we want to hold on to our variable h. So we're not going to use it initially. But this information is important, though, because notice the information given to us, h and dH dt, these are all h related, which means that the most efficient path to our answer is if we get our equation in terms of h, and that way the h and dH dt will just naturally show up for us to use. So what that tells us is that we want to find a replacement for r. We want the r to be replaced. So I'm going to solve for r here, so I can replace that r. Divide both sides by 20. So this is going to go in place of r. Okay, so here's my updated volume equation. R squared h. Okay, questions so far? Okay. We do want to find the derivative eventually, but not yet. Okay, let's clean this up all the way to the point where we have an easy power rule to apply for this volume equation. So we're going to square this expression. We're going to clean up, push the coefficients in front, combine the variables together. So 3 times 4 is 12. I can push that out in front. The h squared and h can be combined to be h cubed. Okay. Now I'm ready. Now I'm in a better position to have an easy go with my derivative. Okay, so here's my derivative. V becomes dv dt. Pi over 12, coefficient is going to stay. And then h cubed, right, power rule, 3h squared. But we also need what after that? dh dt, right? Every variable has time, has a time impact. Right, if you look, we have everything that we need, right? H 8 dh dt is -1/2, so we're kind of looking ahead, and we planned ahead to allow for a nice transition for what we need. So do a little, so I can start plugging in, right? I have all the information that I need here to get my dv dt variable. Everything is on the right side. We can just clean that up and get down to a number, and that's our dv dt. Okay, cleans up to be 1/4 times 64, which is 16. 16 divided by 2 is 8, -8 pi. Units of measure, cubic feet per hour. Any questions here? Okay. Now, if you look at the answer choice doesn't have -8 pi. It only has 8 pi. But that's the answer choice that we choose because it doesn't say -8 pi, but it does preface it by saying that water is leaving. So I think that leaving is an indication that we're dealing with a negative rate. So that accounts for, so that's consistent with our answer. So we can either say the volume is changing at a rate of -8 pi, or we can say that water is leaving at a rate of 8 pi. Those are consistent. Okay, so those are the big related rates problems I want to go over with you. Any questions? Okay. I want to spend the remaining time going over derivatives. So let me put an example for us to try here. So let's say our f prime graph looks like this. And what I want us to be able to do is to be able to look at an f prime graph and gather all the information about the f of x function, where the relative max, relative min, point of inflection, concave up, concave down, increase, decrease. So we want to be able to find relative extrema, intervals of increase, decrease, point of inflection, and concavity intervals. and then also to be able to sketch f of x. So you may need to do this. Well, on the exam, is most you may have happen is you have the f prime graph. It's asking you for information regarding max, min, increase, decrease, or you have to be able to match with the appropriate f of x graph. Okay, but we're going to just treat it like as if it's an open response and then kind of see all the steps that can go into getting to our answer. So the first thing to realize is that this is not the shape of the original graph. Okay, the reason why is because the points that you see do not correlate with the positions of the graph. They correlate with the slope values of the graph. So to help us make sure we are clear with that idea, I like to go ahead and mark up my diagram. I know that anything above the x-axis is going to correspond with where my original graph is going to be displaying positive slope. Anything below the x-axis is going to correspond with negative slope. Anything on the x-axis is where I have slope 0. So I'm going to create a slope sine line to kind of, so I can see an idea as to what my original graph may resemble. So where are my critical points going to be? Good. So where slope 0 is where I'm targeting right now. Okay, from here, we're going to determine whether our graph is part of positive slope or whether it's part of negative slope. But we don't want to look at the slope of the f prime graph. We want to look at the location. So that's where this helps us out, right? All this, even though this looks like positive slope, all these are just different variations of negative slope. Okay, some steeper than others, but these are all negative slopes. So we want to correspond anything to the left of -1 as negative slope. Okay, between -1 and 1, these are all displaying locations where we're going to see positive slope. Between 1 and 5, these are all places where I have negative slope. And to the right of 5, positive slope. Now, once I have my arrows showing in my sine line, I can pull all the information that I need from the regarding slope, right? Relative max, relative min, increase, decrease. So let's go ahead and find all that information. Increase intervals are these two intervals. Okay. Decrease intervals and then we can also gather information about relative max and relative min. Okay. We don't know the y values, but we do know the x values. Relative max is at x equals 1, and relative min, -1 and 5. Okay. All right, let's gather information about concavity based off the f prime graph. So let's create an f double prime sine line. And how do we pick out critical points from the f prime graph to fill out the f double prime? Where can we find points of inflection?
Where f prime of x changes.
Okay, more specific. So where were we looking?
Like -1.
Okay, so we found that from here, right?
Oh, sorry.
So someplace else. Okay.
0.
Yeah, where max and mins are. Where max and mins are. So these are places, your peaks and valleys are going to be where points of inflection is going to live. And the reason why is because points of inflection on the original graph is where your maximum and minimum steepness occurs. So because we're looking at f prime graph and we're dealing with slope values, max and mins will be where our points of inflection of our original graph will occur. So 0 and 3. Okay. Now to determine concave up, concave down, now we look at the slope. You see how this is positive slope? But this positive slope is indicating where the slope is becoming more positive. So wherever the slope is becoming more positive, graphically, it's going to exhibit concave up shape. Wherever the slope is becoming more negative, that's going to end up exhibiting in a concave down shape. And then wherever I have concave, wherever my graph is increasing, my f prime graph is increasing, that's why I have concave up. Okay. Any questions here? Okay, let's gather information about point of inflection, concave up, concave down. So concave up, we have 2 intervals of concave up. The middle interval is concave down. And our points of inflection, okay, we need change in signs, and we have that, right? Change in sign here, change in sign here. So both of these critical points are confirmed points of inflection. Okay, questions here? Now let's see if we can sketch a graph of what the original graph could look like. Okay. Maybe our y values may be different, but we should all be able to achieve the same shape graph. So as I build my graph, I'm just going to look at these arrows. These arrows are going to help me shape my graph. So I want to create a situation where there's a relative minimum at -1. So relative minimum is I like to think of it as just a lower point on the graph. So I'm just going to target a relatively low point on my coordinate plane. Okay. I want to achieve a relative max at 1. So I'm just going to arbitrarily choose a point that's relatively high. And then 5 is a relative minimum. So I want that to be a little bit lower. I don't know the curvature of my graph, but I'm just going to lightly sketch where my max and mins are going to occur. Once I have my path, I'm going to mark where my points of inflection could be. So somewhere at x equals 0, and then at 3. And these are going to be my target points to help me decide where my curvature is going to change, right? Because these are points of inflection. So up until 0, I want concave up. So I'm going to retrace the graph and kind of exaggerate my concavity here. From 0 to 3, I'm expecting concave down. And from 3 to infinity, concave up. So these are what actual points of inflection looks like. So if you look at points of inflection, these are places where technically the steepest part of the graph is going to exist, right? So that steepness is a maximum steepness, and that's why it shows up as a relative max on the f-prime graph. Here, this is a minimum steepness, could be like -3 or -4, and that's why it shows up as a relative minimum on the F prime graph. Okay, questions? Yeah, so those are the topics that I want to be able to get through today. And then tomorrow, maybe we can hit some of Chapter 3's theorems. We can review some of the concepts from Chapter 5, maybe log differentiation, just some miscellaneous things from Chapter 5. Okay. Other than that, hope you guys have a great day. See you guys tomorrow. Be on Teams.